Hi, this is Tony Prescott, and this is a short lecture for COM 3528 at University of Sheffield, Cognitive and Biomimetic Robotics, on the topic of Braitenberg's vehicles. Valentino Braitenberg was a neuroscientist and neurophysiologist, spent most of his life doing experiments to understand how the nervous system works and how brains control behavior. But he's also, by his own description, a synthetic psychologist, so interested in how you can synthesize or build models of animal behavior and animal nervous systems. And he's well known in AI and robotics for writing this short book, Vehicles, Experiments in Synthetic Psychology. And this book is really a series of thought experiments about the behavior that you might create if you built some very simple vehicles and wired them up in an appropriate way, in a way that's inspired by what we know about animals and animal nervous systems. And the book has a number of take-home messages. One of them is that when we analyze a mechanism, such as a mechanism that we find in biology, for example, nervous systems, then there's a tendency to overestimate the complexity. And the second take-home message, which kind of comes from that, is that this task of analysis, trying to understand a complex system by observing it and doing experiments, is really quite difficult. And another approach to understanding intelligent systems, such as animals, is to try and build something like them, so to invent things, to synthesize things. And Braitenberg put forth this idea that analysis was an uphill task, a struggle, and that invention in some ways might be a bit simpler, a downhill task. He called this the law of uphill analysis and downhill invention. Actually, invention can be hard too, but in different ways. And maybe the way that we want to think about these things is that analysis and invention, analysis and synthesis really complement each other as approaches for understanding intelligence. So Braitenberg's book is based on this idea of building simple robot vehicles. The core idea of a vehicle is that you have something which has motors. Let's imagine a vehicle with two driven wheels. Each is separately driven, so you can drive them at different speeds. And the robot will move in a trajectory depending on how fast the wheels are turning. If they're both turning at the same speed, it will move in a straight line. If one's going faster than the other, it will turn in the direction of the wheel that's going slowest. And what drives the speed of the motors is signals coming from sensors, and the sensors respond to sources. So here I've drawn a light source. The idea is that the stronger the stimulus at the sensor, perhaps the faster the wheel will go. So we can say that the stimulus at the sensor excites the motor to go faster. And you can imagine also that this will depend on the distance to the source. So if you're close to the source, you have a stronger signal, a stronger stimulus, and then a faster response. If you're further away, you have a weaker stimulus and a weaker response. And what we're interested in is building these simple vehicles and understanding what they'll do. And sometimes it's easy to figure that out through a thought experiment. Sometimes it's a bit less intuitive, and a simulation helps. And to help understand what these simple vehicles might do, I wrote a simulation environment quite some time ago now in an AI programming language called Lisp, and I simulated Braitenberg's vehicles. And this is a simulated environment with some simple vehicles in it. You can see that each of these vehicles has multiple sensors, and the sensors respond to different sources. There are yellow sensors for the yellow sources, green sensors for the green sources. The blue sensors are for other vehicles. And the behavior of these vehicles is actually quite rich. They are responding, it appears, to the sources in the environment, potentially to each other as well. And understanding what's going on here is a little bit complicated. So what we're going to do is to synthesize these vehicles, starting with something much simpler, and build them up and try and understand how they work that way. So in his book, Braitenberg described vehicle type 1 as the simplest kind of vehicle. The idea is that vehicle 1 just has one sensor and one motor. It has a direct connection between the sensor and the motor. If that's an excitatory connection, then the more stimulus you get at the sensor, the faster the wheel will go. But you can also imagine having an inhibitory connection. So the more stimulus at the sensor, the more inhibited the motor will be. If you imagine you start off with some positive energy in the motor, then the inhibition will slow it down. And we're also going to imagine that besides having sources which might be stationary in the environment, we might have moving sources, and those moving sources might indeed be other vehicles. So if you detect another vehicle, you can respond to that using the right kind of sensor. So let's put some of these vehicles in a simple environment. So this is a vehicle 1. Actually, there's two different varieties of vehicle 1 here. They are both responding to these yellow sources. Let's think of them as light sources. And there's an excitatory connection. So the closer the vehicle is to the source, the stronger the signal is at its sensor, and the faster its wheel will go. Now, if you look at these two vehicles, they seem to be behaving quite differently. The one that is sort of pink or a lighter color with a green triangle in it is doing fairly straight line movements. It has a rather smooth trajectory. The one that is red with the blue triangle is doing much more erratic movements. It seems to be a lot less clear about which direction it's trying to move in. Both of them are speeding up when they get close to the source, which is what we would expect because we wired it up so that the stronger the stimulus, the faster the motor would go. Actually, the only difference between these two vehicles is that the darker one has some noise in it. So I modeled the connection between the sensor and the motor, but I added some sensory noise so that the signal at the motor wouldn't be exactly proportional to the signal at the sensor. It would be that plus some noise. And that's giving it this erratic behavior. There's also some motor behavior. So that means, if you like, it maybe has a wobbly wheel, and so it doesn't always go in a straight line. So this vehicle with some noise in it has different behavior simply because it is noisy. In a way, you could say that the behavior of that robot is richer. But we know, because we built it, that it's just noisier. So noise in itself could generate behavioral complexity, behavioral richness. Let's think about what would happen if we have an inhibitory connection between the sensor and the actuator. So these two vehicles are the same as the previous one, except that we've replaced excitation with inhibition. We've given the vehicles some default amount of forward movement so that they'll move in the absence of a source, but they'll now slow down in the presence of a source. So you can see they're going quite quickly, but they get close and they slow down. Again, we've got one which has no noise in it, and that one will slow down and stop close to the source. The one which has noise in it, it has the wobbly wheel, it will eventually move away because of noise. So it will approach the stimulus and it will slow down, but it will eventually disappear off because of the perturbation we've given it. Now let's put this same kind of sensor-motor relationship, but into robots or vehicles that respond to each other. So these are vehicles that have an excitatory connection. You can tell that because when they get close to each other, they go faster. There's a bit of sensory or motor noise, so that there's a bit of wobble, so they don't go exactly in straight lines. What you see is that the vehicles slow down when they're away from other vehicles. They speed up when they're close to each other. They sometimes have collisions and they bounce off each other. You see also that I've modeled a wraparound world. They go off one side of the world, they come back on the other. So what's interesting here is that because of this simple mechanism, we just connected a sensor to a motor. On average, the vehicles spend more of their time away from each other in open space because they speed up when they get close, they slow down when they're further away. So you could say that these vehicles have quite a clever strategy for staying in open space. Perhaps they prefer to be socially distant, if you like. But we've done that in a very simple way. We've done that just by building the simple excitatory relationship between proximity to another vehicle and how fast the motor goes. So Braitenberg talked about these Type 1 vehicles, and he imagined possibly seeing one in nature. So imagine now what you would think if you saw such a vehicle swimming around in a pond. It is restless, you might say. It doesn't like warm water. But it's quite stupid, since it's not able to turn back to the nice cold spot it overshot in its restlessness. So not intelligent, but interesting. You might say it's alive, since you've never seen a particle of dead matter move around quite like that. Well, I don't know if you would think that these vehicles could be anything like alive. We've obviously just simulated them in a computer. But if we look at the kind of life that you do see in ponds, and this is a video of some pond animals. These are actually water fleas, Daphnia, and they look not unlike the behavior they're exhibiting is not unlike the behavior of our vehicles. They seem to speed up when they're close to each other, spend a bit more time in open space, and they drift about or they move in a roughly straight line. And these aren't simple animals. They're very tiny, just a few millimeters, but they have multiple internal organs, they have sensors, they have nervous systems. But the behavior that they express is, on one level, not that much more complex than the behavior of our simulated vehicles, which have no nervous system at all. And this is Braitenberg's lesson, that when we analyze a mechanism, we can overestimate its complexity. So we may be overestimating what the nervous system in these animals is doing. It may in the end be doing something relatively simple in terms of how it drives the animal to move around in its environment in relation to the stimulus that it has from other objects in the environment, particularly other animals. So that's vehicle one. But we can build more complex vehicles very easily. And vehicle two we can build just by taking two of these vehicle ones and gluing them together. You could imagine some scenario in evolution. Two vehicle ones collide together and stick, and that makes a better vehicle, and so they reproduce. You have vehicle two. And we have different species of vehicle two. Vehicle 2A has these excitatory connections where the sensors just talk to the motor on that same side. We'll call them uncrossed connections. But we can imagine vehicles that are the same, but the connections cross. So the left sensor talks to the right wheel, the right sensor talks to the left wheel. And we can also imagine perhaps having both sensors talking to both wheels. We'll call that vehicle 2C. We'll call the cross connections 2B, the uncrossed connections 2A. Now we can do the thought experiment. What will happen when these vehicles are put in an environment? So let's say that the sensors are responsive to light. And let's try vehicle 2A. Well, we said that the stimulus on the sensor, the strength of that depends on the distance to the source. So we've put a vehicle close to a source, but one sensor is a bit closer to the source than the other. And that will generate a difference in the amount of activity in the sensor and in the corresponding amount of activity going to the wheel. In this case, the sensor that's closest to the source, we'll call that the inside sensor, is talking to the wheel that's closest to the source, we'll call that the inside wheel, and sending it more excitation. So it's going to go faster. The outside sensor talking to the outside wheel is sending less excitation. That's going to go slower. If the inside wheel is going faster, then that means that the vehicle is going to tend to turn outwards. And that will take it away from the source. So we can say that 2A spends more time where there is a lower concentration of the stimulus and speeds up when there's higher concentration, so it goes faster as it comes close to the source. But unless the source is straight ahead, in which case it will go directly towards it, it will tend to turn away when it's slightly off to one side relative to the source. Now, if we think about the vehicle with cross connections, it's the same story. It will tend to speed up as it comes close, but will have quite the opposite behavior because of these cross connections. So the signal that is going to, that is strongest is to the inside sensor, but that's now going to the outside wheel. The outside wheel will go faster than the inside wheel, so the vehicle will tend to turn towards the source. So it will turn towards the source, it might even bump into it. So here we have 3 of these type 2 vehicles in a simple environment with a single source. And let's try and work out which is which. So first of all, the uncrossed connections. So remember we said that the inside sensor talks to the inside wheel. If it's getting more stimulus, that means the inside wheel goes faster. That means the vehicle turns out. Now, if we look at these vehicles, we can see the blue vehicle here is tending to turn away. So it's speeding up, but then turning away as it comes close to the source. So that must be the uncrossed connections. So what about the cross connections? Well, we're looking for a vehicle that speeds up as it comes towards the source, but then turns in towards the source because the inside sensor is talking to the outside wheel. That's causing it to turn in. If you look at the green vehicle here, you can see that's turning in. It had a collision there, but it's on. Usually it will turn in towards the source. So it looks like the green sensor is our type, the green vehicle is our type 2B. And Braitenberg talked about these type 2 vehicles. He said 2A and 2B both seem to dislike sources because they speed up when they get close. 2A shows fear, he said, because it turns away. 2B shows aggression. There you saw 2B crash into the source. And so that's one way of describing what they're doing. Of course, it's just simply sensors connected to motors. There's no real emotion inside these systems. But again, if you saw this behavior in an animal, you might tend to read more complexity into its behavior than perhaps is really there. What about 2C? Well, 2C is the light blue robot, and as you can tell, it's just going more or less in a straight line, barely deviating to the left or right. There's a bit of wobble in the wheel perhaps, but it's not being affected by the proximity of the source. It's quite boring and uninteresting, this vehicle, despite the fact that it has more connections than either 2A or 2B. And in fact, vehicle 2C is just, if you like, the luxury version of vehicle 1. Because both sensors talk to both wheels, the fact that they are spatially separated makes no difference because the signals at the wheels are added together. So there isn't any difference in how the two wheels drive relative to the position of the source. So this is one of the lessons from Braitenberg's book, that the complexity of the system that you observe doesn't necessarily correspond to the richness of the behavior. Here we have a more complex system to look at, more connections, but less rich behavior than in either the 2 other type 2 robots, which only have the 2 connections. So we could do the same trick with this vehicle that we did with vehicle 1. We can swap excitation for inhibition. Braitenberg calls these vehicle 3. 3A has the uncrossed inhibitory connections. 3B has crossed inhibitory connections. Again, we can do the thought experiment. What happens when these vehicles approach a source? So 3A, well, now it's the case that the inside sensor is driving the inside wheel, but it's inhibiting it. That means the inside wheel is going slower than the outside wheel. That means turning in towards the source, the opposite of what we had with the excitatory uncrossed connections. And with the crossed inhibitory connections, the inside sensor is driving the outside wheel, but it's inhibiting it, so the outside wheel is going slower. That means that this vehicle will slow down as it approaches the source, but it will turn away. So both of these vehicles are going to slow down as they approach, but one's going to turn in, the uncrossed connections, the other one is going to turn out. So we can verify that in our simulation. So we're looking first of all for the one with the uncrossed connections. So the uncrossed connections, as we said, that's going to be the one where the inside sensor drives the inside wheel, inhibits it. That means it's going to turn in. That's clearly going to be the blue vehicle here. The cross connections is going to be the one where the inside sensor is inhibiting the outside wheel. That means that the inside wheel drives faster. That means that the robot is going to turn away. That's the green vehicle in this experiment. So Braitenberg says that 3A and 3B both like sources. What he means is that they go slower close to sources, so on average they spend time nearer the source than away. 3A loves the source. What he means is that it slows down, and we've designed it so it stops near the source. 3B is more of an explorer. It comes towards the source but slows down and eventually moves away. Now we can think about putting lots of different sensor types on our vehicle and making each sensor pair sensitive to a different kind of source. So let's have yellow sources, we'll think of those as light. Red sources, we'll think of those as heat. Oxygen, we'll think of as blue source, and organic matter we'll think of as a green source. So, and here we have vehicles with sensors for all these different kinds of sources, and they are moving around and responding to the different sources in the environment. So if we look at this, it's quite a complicated setup. We've got several vehicles, we've got lots of sources. The behavior is quite difficult to analyze. We're getting to a point where our analytical skills are stretched just from observing behavior. What can we do? Well, because the behavior is complicated, one strategy is to simplify the environment. And that's what psychologists do when they do experiments. They simplify the world, or they compare between two conditions where they just change one thing in the world, and that's called a controlled experiment. And so we can do some controlled experiment. The simplest thing that we can do is to take all the sources out of our simulated world and see what happens. So here we have our vehicles in a completely empty world. We see that what happens is that the vehicles move more or less in a straight line. There's maybe a bit of wobble in the wheels, but they are moving at a constant speed in the absence of any sources. So we know that the default behavior for these vehicles is to move forward. We know from this as well that they're not responding to each other because the presence of nearby robots doesn't seem to affect the trajectory. Then we can add a light source, and we can see what happens with the light source. So you can see straight away that the robots are speeding up slightly when there's a light source, and also turning towards the light source, so certainly when they're moving towards it. So here we have one which is approaching head-on. Hard to tell very much from that, but here's another one approaching to the side, and you can see it's turning in towards the light source, just missing colliding with it. So these are vehicles. There must be an excitatory connection for light, and it looks like it must be the crossed connection because that's the excitatory connection that gives you this turning in behavior. What about the red source, the heat source? Well, if we watch these robots again, if we watch them carefully, we can see they're speeding up a bit as they get close to the source. As they get very close, they seem to be turning out a little bit. So that suggests that the wiring diagram is the opposite. So it looks like the inside wheel is driving, the inside sensor is driving the inside wheel to go faster. That's making it turn out. So this looks like the excitatory uncrossed connections. So now let's look at the blue sources, what we called oxygen. So here we can see that the robots are slowing down a little bit as they get close to the source, and they're clearly also turning away from the source. So if it's inhibition because they're slowing down, then that means that must be cross connections. So the inside sensor is inhibiting the outside wheel. That means the inside wheel is going faster and they're turning away. And finally, the green source, what we're calling organic matter. Well, we can see that the vehicles are slowing down and stopping when they come close to the source. They seem to be turning in towards the source. That means that the inside sensor must be driving the inside wheel to go slower. That must mean the uncrossed inhibitory connections. So by doing these controlled experiments, we've been able to work out exactly how this vehicle is wired up, how each of the sensors responds, drives each of the motors, what kind of connections they have. It's quite like the Type 3 vehicle that Braitenberg describes in his book. I've actually swapped the oxygen and the organic matter compared to the book. In his book, Braitenberg describes vehicles that stay in areas of high oxygen, move towards organic matter, but can be distracted by a larger source, avoid areas of high temperature. Well, they speed up when they're close to heat sources and turn away and attack light sources. So you can see they turn in and bang into the light sources. Braitenberg talks about these vehicles as having values, or certainly having preferences. They seem to be preferred to be close to the green and the blue ones, and to move quickly and away from the red ones, and to crash into and try and destroy the yellow ones. So, but we know that they're just sensors connected to motors. There's no nervous system, there's no control system really other than these direct connections. So this idea that they have values is something that we're reading into the behavior. We're reading in more complexity than we know is there. So we can make these vehicles have richer behavior, still without adding any extra activity, any kind of nervous system inside the vehicle, and just by changing the nature of the relationship between stimulus intensity and motor speed. So far we've been looking at vehicles where there's a linear relationship, a straight line relationship between stimulus intensity and velocity. So if it's excitatory, the more intensity you have, the faster the wheel will go. So that's a straight line going upwards. If it's inhibitory, the more intensity you have, the slower the wheel will go. That's a straight line going downwards. But we could imagine non-linear relationships. We could have a simple step function that I've shown here in the middle. That's where there's no change in the velocity of the wheel as the stimulus intensity increases, but it gets to a threshold and then it jumps up to maximum speed. Or we could imagine a smoother non-linearity like this non-monotonic function, what we might call a bump function, where the speed of the wheel increases with increasing intensity for low intensities, but beyond a certain point, the speed decreases with the increasing intensity. And animals seem to have this kind of relationship, because if you think about simple single-celled animals, for instance, they tend to have preferences for certain intensities of heat or light or temperature. So they like it to be hot but not too hot and not too cold. They maybe like to have a certain amount of salt in the environment, but not too salty, and no salt whatsoever. And the way you get into those sort of Goldilocks zone is to have these kinds of preferences, to go fast when it's too salty or not salty enough, and to go slowly when it's just right. So a bump function or an inverted bump function. So we can look at putting these kinds of functions into our vehicles. So we'll take vehicle 2B, which had the cross excitatory connections, and we'll just replace linear excitation with this this bump function. So let's do the thought experiment. So imagine the vehicle is quite close to the light source. Then the sensor which is closest to the light is going to get less excitation. It's at the lower down on the slope than the sensor that's further away from the light source. That means, because there's cross connections, that the inside wheel is actually going to go faster than the outside wheel. That means that the vehicle is going to turn away from the light source when it's close to the light source. Now think about what's happening when it's far away. Now we're on the downward slope of the bump function. That means the inside sensor is going to have more stimulation than the outside sensor, the opposite than when we were close. And that means that the inside sensor, which is driving the outside wheel, which is going to go faster, that means we're going to turn in towards the stimulus when we're further away. What does that mean for the behavior of the vehicle? Well, we've done the thought experiment, but let's do the simulation. And what we're going to do now is put this vehicle into an environment with two light sources, just to make it a bit more interesting. And what we see is that this vehicle likes to circle around these light sources. In fact, it describes this elegant sort of figure of 8 movement. And it does that because we know that when it's too close to the light source, it tends to turn away. But when it's too far away from the light source, it tends to turn towards the source. So that's a nice way of generating quite a rich behavior from really just a simple vehicle, but using this non-monotonic function. Now, what if we were to swap these uncrossed connections for cross-cut connections? What will happen? Well, here's the simulation. I've put in 6 identical robots here. Now, when in the previous robot, it tended to turn away from the source when it was close to it, and towards the source when it was away. And these robots which have the uncrossed connections do the exact opposite. So when they're away from the source, they tend to turn away, and when they're close to the source, they tend to turn in. And of course, they're going to spend most of their time away from the source because they don't seem to want to approach it. But when they do seem to approach it, then they sort of swerve in and almost seem to attack it. So they don't seem to like the sources, they avoid it, but when they do get close, they turn in and seem to approach it. So quite an interesting behavior. But now imagine that if these sources were other robots, what might happen? So let's do the same experiment, but rather than have static sources, we'll have these vehicles with these uncrossed bump functions, and we'll make them respond to other vehicles. So that means that when the vehicle is far away, they'll turn away. When another vehicle is nearby, they'll turn towards it. What happens? It's difficult to do the thought experiment, but we can do the simulation. So what we see in this simulation is this a nice immersion effect that the vehicles tend to avoid each other most of the time. So when they're far away, they tend to be turning away. But when they get close to each other, they tend to turn towards the other vehicle. And as a consequence of that, they tend to stop following each other, and you actually get these little chains of vehicles, one following another, and then another one might follow that one and build a longer chain. It looks a little bit like a social behavior. The robots are teaming up and forming these conga lines. But we know that these robots don't have anything more sophisticated than these uncrossed bump connections. That's all that's generating this behavior. So this sort of apparent social behavior is, if you like, emergent property of this system that we've simulated. Now, Braitenberg's book goes on to describe lots of other vehicles. Vehicle 5 in the book, he adds interneurons. So he adds some units that sit in between the sensors and the motors, and they can do things like logic, and they can do things like memory, so that they can record past sensor values. Once you start to do that, you effectively put a neural network inside your robot, and it can do all sorts of interesting things with the sensor signals and using those to control the movement of the wheels. Another idea is that you could take lots of vehicles and you could randomly wire them up, and you could set them a task. Say the task is to stay on this tabletop, and when a vehicle falls off the tabletop, you just take the parts of it and you use that to build another vehicle. But you do that in quite a sloppy way, so sometimes you don't copy it exactly. Actually, what you do is you take one of the vehicles that's still on the table and you try and copy that, but you don't bother to do it as exactly as possible. You might make a couple of small changes. If you do that, then you have a form of artificial evolution. The vehicles that stay on the table tend to get copied. They don't get copied perfectly. Sometimes the changes lead to a better vehicle. Sometimes they don't. The ones which are better stay on the table more effectively. Over time, you get vehicles that are good at staying on the table. You've got a kind of artificial evolution. And we saw in one of the earlier lectures how people have used artificial evolution to develop neural network controllers for simulated vehicles. We looked at Carl Sims, who did these jointed, if you like, robot vehicles in full physics simulations, and showed how you could evolve controllers which would generate swimming or walking depending on what challenge you gave them. So Vehicle 6 is really quite a general purpose way of designing vehicles that over time can get better and better at different sorts of tasks. And if you look at the book, and it's well worth reading, there are several more chapters describing vehicles of more complexity, ones that have more sophisticated sensory processing, for example, in Vehicle 8, I think it is. So please go off and look at the book. Just to summarize what we've covered here, the key lesson of Braitenberg's vehicles is that when we analyze a mechanism, there's a risk we can overestimate its complexity. When we look at something that nature has built or that someone else has built, it's hard to figure out how it works. Sometimes synthesis is easier. We can try and build something that does the same thing, and from that synthetic process, that invention process, we can understand what it takes to solve that problem. But more generally, synthesis and analysis can work side by side for understanding complex systems like animals. We can analyze the existing complex systems. We can try and synthesize artificial systems that are similar. And we've seen also that the behavior that emerges from any kind of complex system depends on the interaction with the environment. And if the environment is richer, you can get more interesting and richer behavior. You can even get what appear to be social behaviors where the other things in the environment are themselves vehicles, and you're responding to those vehicles and they're responding to you. That sort of complex dyadic interaction, which is hard to do the simulation in your head, but we've seen that when you simulate even simple vehicles that respond to each other, you can get some interesting, almost social behavior. So that's it for this talk, and just want to finish by just remembering Valentino Braitenberg and the great contribution that he made to science and to this idea that we can synthesize vehicles and robots, and we can use this synthetic approach as a complement to neuroscience and biology to understand complex systems, including ourselves. Thank you.